So this video serves as an introduction to waves. So what are waves? Well, a wave is some type of disturbance, whether that be from the wind, like in the ocean, or from somebody pushing a slinky back and forth. And what waves do is they actually transfer the energy around them. Most waves need something to travel through, and so this substance that the waves travel through is what we call a medium. Most mediums are like a solid, liquid, or gas. So if a wave requires a medium, then it's called a mechanical wave. If it does not require a medium, then it's going to be an electromagnetic wave. And that's going to be a topic for a different day. So this video is going to focus on mechanical waves. Mechanical waves create vibration. So this is going to be like a repeated up and down pattern or a repeated back and forth pattern. So let's go ahead and talk about the three different types of mechanical waves. The first one we're going to look at is a transverse wave. And this is a wave that vibrates in the medium at right angles or perpendicular to the direction of the wave. So let's go ahead and see a picture of that. So here we have a transverse wave. And as you can see, if you pretend that you are the one who is shaking the rope, you are shaking the rope up and down. But the direction that the wave is actually traveling is to the right. So if you're shaking the rope up and down, but the wave is traveling to the right, those are perpendicular directions. And that's the definition of a transverse wave. The next type of wave that we're going to talk about is a longitudinal wave. So this vibrates a medium in the same direction in which it travels. So let's look at a longitudinal wave. So as you can see, the hand is pushing the slinky back and forth, back and forth. And the direction of the wave, if you follow the compression from like point A to point B down here, the direction is to the right. But then it's also, the hand is actually going to the right and to the left. So it's in the same direction that the wave is traveling. And so this is a longitudinal wave. A sound wave is an example of a longitudinal wave. And lastly, we're going to talk about a surface wave. A surface wave is kind of a combination of a transverse and longitudinal, but the main difference, and this is the reason why they're called surface waves, is because they actually separate two different mediums. Let's take a look at a picture of a surface wave. So here is a surface wave. You can see that there is air on the top and there is water at the bottom. And so because this is a separation of two different surfaces, that's why we have a surface wave. And if you think about the medium that it's traveling through, okay, if you were to put a particle in the middle here, like the bottle is actually going to go around in a circle. So it's going to be kind of go to the left, and then it's going to travel up, and it's going to travel back to the right. So it goes like up and down. So it kind of like rolls, if you will. Notice how the bottle stays in the same place, but the wave is actually moving in towards the right. So there are some properties of waves that we need to talk about. So when we're talking about a transverse wave, transverse waves have crests and they have troughs. So a crest is the highest point on a wave. So this would be a crest, and a trough is the lowest point in a wave. So that would be the trough. The rest position is the object's position before it was moved. And so this is usually indicated by this dotted line right here. So if there was no wave in the rope would lie along this dotted line. And that's what we call the rest position. And the rest position is really important to know because oftentimes it's used as a reference point when we talk about some of these other properties. So the amplitude is like how far the medium moves. So if the medium is a slinky, how far does the slinky move back and forth? If the medium is a rope, how far up or down does the rope move? And so this looks a little bit different between transverse and longitudinal waves. So let's go ahead and take a look at that. So here at the top, we have a transverse wave. So the amplitude is how high up or how far down. These two distances are usually the same. And so the amplitude you can measure either from the crest to the rest position or from the trough to the rest position. In a longitudinal wave, it's a little bit harder to kind of figure out because for a longitudinal wave, you would have to look at one single point on the slinky and you would have to measure how far to the right or to the left it travels. But the maximum distance that this little point on the slinky would move, that would be the amplitude. Usually the larger the amplitude for a longitudinal wave, the louder the sound is going to be. Wavelength is the next property, and this is the distance between two corresponding points. And so because this is a distance, we can measure this using any of our units for distance, like centimeters or meters or kilometers. And so between these two waves, this is going to look a little bit different. So for a transverse wave, this is the distance from crest to crest or from trough to trough. For a longitudinal wave, this is going to be the distance between those compressions. So let's go ahead and take a look at a picture of this. So here at the top, we have a transverse wave. So here's a crest and here's a crest. So if I were to measure the distance between these two, that would be the wavelength. You could also measure the distance from trough to trough. These two up here, this point A and this distance B, they should be the same distance, and therefore that would be your wavelength. For a longitudinal wave down here at the bottom, you would take the middle of one compression to the middle of the next compression, and that would be your wavelength for a longitudinal wave. Another property that we need to talk about is the frequency. So this is the number of waves that pass a given point, in a certain amount of time. Usually this is measured in hertz. Hertz just simply means the number of waves per second. So let's take a look at the frequency here. Up here we have a transverse wave, and I've actually put two different transverse waves so that we could talk about the relationship between frequency and wavelength. So notice how at this top picture, this has a very short wavelength. So if we were to look at this point right here, you'd easily be able to tell me that the top would have a higher frequency. There's going to be more crests that pass that point in 1 second than there would be on this bottom wave down here. So again, the frequency is the number of crests or the number of waves that pass this point in 1 second. And so the shorter the wavelength, the higher the frequency. The longer the wavelength, the lower the frequency. If we know the wavelength and the frequency, we can easily figure out the wave's speed. So here's an equation for the speed of a wave. Speed equals wavelength times frequency. So because it's a wave length, it can be measured in meters. And by definition, the frequency is the number of crests per second, so 1 over seconds. So because we have meters over seconds, the speed of a wave is the same unit as the other speeds that we talked about previously. There's another video later on in this unit which is going to show you some example problems. So that's all I wanted to talk to you about waves for now.